Good morning to everybody. In this, my last lecture, I will talk about the present situation and the future in the search for neutrinos double beta decay using germanium 76. So the present means an experiment called Legend 200, and the future will be hopefully Legend 1000. Okay, first of all, what is Legend? Legend stands for Large Enriched Germanium Experiment for Neutrinoless Double Beta Decay, and it is a collaboration. A collaboration now of about 300 persons, so a large for the size of the previous experiment, a large collaboration, 55 institutions from many countries, as you can see. And is the joining of, mainly the joining from the two previous experiments in this field, Gerda and the Majorana demonstrators. So the community is Majorana demonstrator means from United States and Gerda from Europe. Of course, there are also other groups, but the core of this experiment comes from Gerda and Majorana. The collaboration born in October 2016. The mission. The mission is to develop a phase approach to the neutrino double beta decay using germanium 76 with a discovery potential. Then I will return back later on the meaning of this discovery potential. But of course is something that related to the hope to see really a signal, not to put an upper limit. On the half-life, significantly longer than 2027 years, using also the resources already available. So making a good use of the technology available. Okay, this is the program. So as I said, the Legend is the combination or attempt to use the best from the two experiments, the most important experiment, Gerda and Majorana demonstrator. And in this slide, I put what are the best, the best for Gerda and the best for Majorana. The best from Gerda is to have used this bare germanium array. Bare means minimizing the material near the detectors in liquid argon. We have seen that liquid argon is a good shield, which together with pure water in order to reduce the background coming from the environmental. And here you see the amount of mass that we have used in phase 1 and phase 2. The best from Majorana, here you see the sketch, and this is instead a photo of the setup for Gerda. You see this is the water tank, and above the water tank there is a clean room. Okay, this is a sketch of Gerda, of Majorana. I already said something regarding Majorana during last lesson. The more important aspect of Majorana is to have used copper of very high purity. The best copper in the world, electroformed underground, so made by the collaboration itself. The shield is a conventional shield, very compact, made of this electroformed copper and lead, and they use this 30 kilogram of enriched germanium detector. Both had the goal to scrutinize the degenerate mass range, so the upper part of the M beta beta range, and in some sense both have made important study with development the development of the technology in order to suppress the various type of background. From the very beginning, so from the foundation of this distinct collaboration, Gerda and Majorana, they have realized from the very beginning that it is fruitful to exchange technology experience, even if at certain point each experiment goes from its particular path. But from the very beginning, there was a joining of activity between the two collaboration. For example, we developed the same structure of the Monte Carlo simulation called MAGE, because Monte Carlo, as you have realized, is very important to have the same Monte Carlo can improve the performances of each experiment and also pave the way for a future union of the two collaboration. And in fact, in the letter of intents of both experiment, it was written that, well, if the program of Gerda, for example, I am saying Gerda, after phase 2, we don't see anything now. At that point, the only possibility, if one has to go further continuing in this field, is to make a huge experiment, a ton, 1 ton experiment using germanium 76, but 1 ton of germanium 76 is a huge effort, and only having a real international collaboration, this is the only possibility to have a success in this direction. And for that reason, for the very beginning, both collaboration had this goal to join sometimes in the future. Okay. So, as I said at the beginning, the Legend program has in its heart the idea of a stage approach. So it is not possible to jump to this big, enormous experiment with 1 ton of germanium 76 in a single jump, but it is necessary to make a stage approach for many different reasons, because it's difficult, simply difficult to make this enormous jump, and also it is good to produce physical result in the meantime. Okay, and the first step of this Legend research program is called Legend 200. Legend 200 is an experiment at the Gran Sasso Laboratory in Italy, which use the infrastructure of Gerda. And so Legend 200 is hosted in the Gerda infrastructure. So it uses the same cryostat, the same water tank, the same clean room of Gerda. We did only the upgrade of this existing infrastructure in order to host, to be able to deploy inside the cryostat 200 kilogram of germanium detector. I remind you that Gerda deployed in the second phase, 40 kilogram of enriched germanium detector, and Majorana demonstrator use 30 kilogram of germanium detector. So to reach this 200 kilogram of mass, Legend 200 use the mass, the detector of Gerda, the detector of Majorana demonstrator, and the remaining part are new detector produced for this new experiment, 140 kilogram. But as I have shown yesterday, and already said also by JJ, all the experiment now in this field have realized that it is important in order to produce a boost in this search. It is important to work in the so-called background-free regime, because in this case the half-life is directly proportional to the exposure and not to the other low power of instead of 1 for the exposure. So we enlarge the mass from 30 kilogram to 200 kilogram. This is fine, but in order to remain background free for the entire data taking, you have to reduce the background. So you have to fight against the background. And the goal of Legend 200 is to reduce the background index of a factor 5 respect to the Gerda phase 2 goal. Gerda phase 2 goal was to reach 10 to minus 3 counts per keV per kilogram per year. So now the goal of Legend 200 is to reach 2 times 10 to minus 4 counts per keV per kilogram per year. So only an improvement of factor 5, which is not enormous, but you have to realize it's not for free, even if it's only a factor 5. Okay. Okay. This is the first stage. The second stage, and if you want the final one, is Legend 1000. 1000 means that we will use at the end 1 tons of germanium detector. This will be a completely new detector, because 1 ton of germanium detector can't be hosted in the Gerda setup. So you have to build a new detector. This new detector costs a lot, because 1 ton of germanium, enriched germanium detector cost, really. This is an experiment which costs a lot. It is important to have money, a lot of money, and so it's not an easy task. Anyway, this experiment, at least as a conceptual design, was approved by the DOE, is approved also by INFN in this conceptual design phase. So it had first green light, and this green light means that all the R&D process can be done. Not the realization of the experiment, because you have to demonstrate other things, but the first brick is there. So in this case, having this in large mass, in order to remain background free for the entire life of this experiment, you have to reduce the background, and you have to reduce the background of a factor 20 respect to legend 200, which means a factor 100 respect to the Gerda phase 2 goal. Where this experiment will be realized, it will be realized now. The preferred site is LGS, so in Italy, while there is also another possibility to install this experiment at Snow Lab, so in Canada, but this is the preferred site, LGS. Okay, now what would be the goal in terms of sensitivity and discovery potential of this program. In this plot here, it is shown in the y-axis the sensitivity. So the half-life in 90% sensitivity level, confidence level expressed in years, and here there is the exposure in ton per year. The various curves that you see here are how the sensitivity develops as a function of exposure and as a function of the background index. The straight line is the case in which you are really background free, so zero background, really no background. And then the other curve are for various hypotheses of background. The red curve, this dashed line in red, is the goal of legend 1000, which is expressed in terms of counts per full width half maximum ton per year, so another manner instead to express in terms of counts per cave per kilogram per year. Okay. And then this band here that you see here, this violet band, is the lower part of the inverted order hierarchy and with its uncertainty. Okay. And then this is what obtained Gerda. Gerda didn't see anything, place a half-life lower limit, upper limit, and for collecting 10 to minus 1 ton per year, so 100 kilogram per year. The goal of Legend 200 is to collect 1 ton per year, which means, supposing to have 200 kilogram, means to run for 5 years. And if you don't see anything, you obtain an half-life of 10 to 27 years. But as you see, you are not scrutinize the entire inverted order hierarchy. You enter in this region, but with Legend 200, but you don't you don't scrutinize the entire region. Instead, the goal of Legend 1000 is to do this, collecting 10 tons per year. So the experiment Legend 1000 has to run at least for 10 years with stable condition, stable background index. And if this experiment doesn't see anything, it will play a sensitivity, it reaches 10 to 28 years, going slightly beyond the lower part of the inverted order hierarchy. Okay. Okay, this is the enriched now. The new detector are a slightly higher fraction of germanium, not more 85 to 87, but 92%, which helps. In this plot, instead, you see the so-called discovery potential. This is another statistical quantity, which say if the experiment will be able to see this experiment, the signal, in the sense that the signal, anyway, it will be very tiny, and it is not so easy to realize in a statistical convincing manner that you are seeing a signal. This discovery potential is defined as a certain definition, common definition, which is gives the discovery potential gives the 50% chance probability to see a 3 sigma a signal to a 3 signal significance. Okay, 3 signal. So this is the definition. Okay, and here you see what will be can be done by these 3 experiments, translating their possibility in terms of this quantity. As you can see, the discovery potential is a quantity more stringent, more difficult to reach respect to the sensitivity. Sensitivity is easier quantity to reach. The discovery potential to reach a high level of discovery potential is difficult because you understand that to be sure that your peak at the Q beta beta is really a signal, the background has to be very, very low. So, and you see, you understand this giving a look to this curve, which has the same amount of are built considering the same background index, but you see that they are worse than this one. They increase slowly than the other. Okay, these 2 plots were realized, were built, assuming an efficiency, a global efficiency, after all, after everything, of 69%, which is not is a goal. It includes everything. I mean, the isotopic fraction, the active volume fraction, all the analysis cut. So it's not for this 79%. And here I have put the various background index in terms of the various Gerda, Legend 200, Legend 1000, in terms of this background index written in this manner. Full width half maximum, of course, is the energy resolution at the Q beta beta, of course. And why this experiment choose this particular background index is to remain background free, which you know is a strong condition for a discovery. A background free means that the average expected background has to be below 1, below 1 event in the ROI, in the range of interest for the entire exposure. Okay, this is, of course, is not easy to obtain. It's not for free. It's a goal, a real goal. Okay, this is what one would like to obtain. Okay, at the end of the story, showing the goal in a different manner, but in a very usual manner, is this one. Here you have the effective Majorana mass in electron volt. Here is the mass of the lightest neutrinos. The green and the red band are the what is allowed from the standard model assuming the present parameter of a mixing matrix and leaving the two Majorana phases completely unknown to go from 0 to pi. The size of this band are due essentially to this unknown of this Majorana parameter. The present limits, the present experiment cover this part. We are entering now in this inverted order hierarchy. JJ will show the result of Kamla and Zen, which are inside this. For example, you realize that Gerda phase 2 reach 80 millivolt as some best limit, so arrives more or less here, so above, not entering inverted order hierarchy. Legend 200 will enter inside. And the target of a next generation of experiment, Legend 1000, for example, is to reach more or less this level, so to cover this entire inverter order hierarchy. Okay, so the first stage. The first stage is Legend 200. Legend 200, as I said, use the Gerda infrastructure, so is similar to Gerda. And here you see how looks like, but then I will discuss later the layout. So the new elements are part of enriched germanium detector, because you have to reach 200 kilogram of mass. There are all the cables, liquid argon veto, front-end electronics, DAC. So the detector inside is new. The experiment start in early 2020, when there was the switch between Gerda and Legend 200. I said yesterday that Gerda ended its data taking in November 2019. The commissioning of this experiment started in November 2021, and in March 2023 we start the first run of physics. Okay, first run, which ended in February 2000. We stopped the data taking February 2024, so roughly 11 months of data taking, the first physics run, and we, at the time, we didn't have the 200 kilogram of germanium detector, but only 140 kilogram. With this fraction of enriched germanium detector. Of germanium 76. The goal of this experiment are the following. This is the goal for what concerns the background index, factor 5 better than the goal of Gerda phase 2. If you run with this background index and you collect 1 ton per year of exposure, and you don't see anything, these are the discovery potential for the half-life, around 10 to 27, and the exclusion is this one, slightly above 10 to 27, so around 10 to 27. Translating this to parameter in terms of m beta beta, this is a result. The uncertainty comes always from the nuclear matrix element. So you enter in the at least with this value inside the inverted order region. The the experiment is this one, is the cryostat and the water tank are the same as Gerda. The experiment is located in the same location of Gerda, so LNGS. The string, the layout of a string are slightly different respect to Gerda. There will be, when we will have all the germanium detector, the 200 kilogram of germanium detector, we will have 12 string, and we have optimized the string and the layout of the liquid argon in order to improve the liquid argon cuts. As you can see here, we will have two shroud of fibers, an inner shroud and an outer shroud, in order to cover in the best manner this germanium detector. The germanium detector are assembled in string with the same techniques, if you want, developed in Gerda, and they are naked. This is an example. And in this part where there is the P+ contact, there is the electronic. Differently from Gerda, here in Legend 200, the front end is on board of a detector, very near to the detector. Instead, in Gerda, the front end was at least 35 centimeters away from the detector. To having the front end near or very near to the detector improves a lot the performances of the electronic. So you reduce a lot the pickup noise. But of course, you have to pay. This is not for free, because the front end is very near to very near the detector, so you have to build with a very clean material, otherwise you are killed. Okay, so this is more or less the new parts. Due to the fact that the liquid argon is improved a lot respect to Gerda, we pay much more attention to the quality of the liquid argon. The liquid argon was selected in order to have a good starting liquid argon. Then it was purified before to be filled inside the cryostat in order to improve their optical property. And also now we have a detector, this one, called Lama, which permit to control online the quality of the liquid argon. So there are various important aspects which improve the experiment respect to Gerda and Majorana. Okay, this cartoon shows what at the very beginning of this experiment we quote as a contribution of a various element to the background budget. This is the background, the contribution of what are the main contributors to the final background index. The goal is at this level to, I repeat, 10 to minus 4. And this is the various contribution. We suppose that the alpha emitter, you don't have, for example, a central value for the alpha emitters, because we think there are only an upper limit, because we are think we'll be able to reject everything. Also, the internal contamination of a germanium detector is very low. We have only upper limits, very, very low, because the purity of this detector is part of their construction. It comes from free, in some sense. And then you see the other contributor. Pay attention to this. You see, this is the beta coming from the decay of the potassium 42. This is, for us, is a possible main contributor. It's a very, very difficult background, which, as we will see also in Legend 1000, we have to pay a lot of attention in order to suppress. Okay, and then there are the usual contributor coming from the infrastructure. So, okay, this is the goal. Monte Carlo, these are only Monte Carlo extrapolation assumption. A word regarding the material. In order to exercise Legend 200 for the final step, Legend 1000, already in Legend 200, we make use of material that could be useful for the last step. For example, we use the underground electroformed copper developed by Majorana demonstrator. Majorana was able to produce copper with an activity which is of this order, so very, 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 both in thorium and uranium. And using this material, we will build the support. We are building the support of the germanium detector. This part, which is the basement of this string column of detector, in Gerda, we use silicon. Now, the idea now, what we are doing in Legend 200 is to use PEN, this polyethylene naphthalene, which is a plastic which can be built clean, rather clean, but the important point is that it is optical active. So it is a scintillating material. And so what it does is to shift the liquid argon scintillation light, which is in a deep ultraviolet region, into a 440 nanometer, which is an infinite, a large attenuation length in the liquid argon, and it can also well matched to the usual SiPM that we are using. And this is not evaluating Legend 200, so we are evaluating their performances, but we are using, okay, as a support, as a high purity detector support and scintillating, in order to don't have shadow in the part, delicate part of our detector. So in order to have light from, or some light from any place around the detectors. Okay, so said this, we, as in March 2023, we start the data taking. We had a total mass of 140 kilogram, putting what we had at the time, of course. So we had a real mass of detector, 4 types of germanium detector: ICPC, BG, PPC. The PPC are point contact detector used in Majorana and also coax detector. This is we know. We accumulated 1 year of data taking, which this means that the exposure was divided depending on the quality of the data. We had an exposure called silver of around 77 kilogram per year, and another subset called golden of 48 kilogram per year, at least for the data that I will show now. The golden data set is the data set used for the neutrino-less double beta decay. Of course, you understand 40 kilogram is an exposure lower than the Gerda phase 2, but this is what we have at the moment. In these two, you see the from one side the calibration run using thorium, the usual one, for the 4 type of detector that we are using, and then here the resolution that we have obtained with these 4 types of detector. Here we have the full width alpha maximum versus energy. The point contact, these 3 curve, show that this detector performed very well. The goal of the Legend 200, but also Legend 1000, is to have a mean full width alpha maximum at the Q beta of the order of 2.5 keV, and you see that apparently we are in the ballpark. The coax, okay, they have worse performance, but we know, and we don't use only now, but not in the future. This is anyway. At least the good detector work in a stable manner, and these are the results. So here I show something that you know already from the previous my lesson. This is the energy spectrum after the quality cuts, the usual quality cuts, the suppression of the background coming from the cosmic rays, and putting this plot only events with an energy release in a single detector. This is what we have. This corresponds to the golden data set. As in Gerda and in Majorana, we blind a region around the Q beta beta in order don't introduce bias in our analysis, a plus or minus 25 keV window. This quality cut, muon cut, and anti-coincidence cut works with high survival of physical events of around 95–99%. Okay, this is the situation, and you see the peaks show the same source of the background. We don't have any new entries. Are all the friends, if you want. The potassium 40, potassium 42, the bismuth, thallium, so, and the alpha components at the high energy. Nothing new, nothing new. Okay, I haven't shown anything last lesson regarding. We understand the energy spectrum, so you understand your data or not? In this plot, there is the comparison between what we have collected with the Monte Carlo simulation. Monte Carlo simulation use, of course, from a side, the geometry, the mass, the knowledge, the primary knowledge of your setup. And then also an input of this Monte Carlo is the activity that we know from the campaign that we did in order to select the material, so we know the activity of a various component. You put this and you do so the activity is in order to have some prior on the various background components. You do a fit and you see if the fit is in agreement with the data, and then you play if there are something that is not well described. Anyway, this is first one of the first exercise due to the fact that here we don't use pal shape cut or liquid argon cut. In this plot, you see that we are using the silver data set, all the data. Okay, you see these are the histogram of the data, and the black histogram is the final Monte Carlo output, and then all the other colored curve, show the various contribution which sum up in order to have this black line. And here there is the residual, and you see that the residual are well distributed with 1, 2 sigma. So this is a good, satisfactory description of this data with the known component. Okay, for the interested, this modeling, background modeling was made using a Bayesian approach, but this is a technicality. The data, at least at this level, so without pal shape and without liquid argon veto, predicts that around the Q beta beta, the background is flat. Okay, at this level, or rather flat. Okay. In effect, I am giving to you only an optimistic view of the problem. In effect, so this is a real fitting. But you could do another, before this, another job. So put what this various background component that you see here, using as a normalization factor the knowledge regarding the screening of the material. And so this is not a fit, it's a real prediction. This is the screening that I have done. There are this and that types of background components, and what happens. If you do this, in theory, you should obtain a perfect description, or rather good description of your data if everything was done in the correct manner. What we have discovered is that if you do this, there is a discrepancies between this prediction based on your measurement of the material and the data. And of course, the situation is that the data are above the prediction, so you have an extra contamination. Unfortunately, what we have discovered that we have introduced the material of worse quality respect to what we had thought. So there is a higher background respect to what we have hoped to have. And this is not, of course, a good thing. Okay, but this is the life. Anyway, as usual, after after what we did, the quality cut, there is the application of a pie shape discrimination, for example. And in green here, you see what remain. There is the suppression of all the alpha particles. And you see also a strong suppression of this part of the energy region, which is the part where there are the Compton continuum of thorium or thallium, even if something remains. Okay. The survival fraction of neutrino-less double beta decay is of order 85%, around 90%. Now, what the last final, last cut is the liquid argon cut. Here I show in a better manner how looks like this new liquid argon instrumentation. So this show how looks like the sketch. You have these are the string of detectors, and inside there is an internal liquid argon veto. Here you see the how looks like this shroud, circular shape shroud of fibers. And then we have an external liquid argon veto here, you see, in order to cover completely the best manner the germanium detector. Here how it looks like. The SiPM are on this side, and also so they are here and here and here. Okay, this is more or less. What are the performances of this liquid argon veto? Well, the performances are better or respect to the Gerda, a factor 3. We have more light. We see more light, both due to the fact that the quality of the liquid argon is better than in Gerda, and also because this detector is better. The argon properties were stable in time, and this is now actively online monitored using a dedicated instrumentation. This liquid argon instrumentation was characterized at the beginning, before the data taking, with spatial calibration rounds, and it is difficult to give a single number to the performances of this type of liquid argon, because the complexity of the detector. Anyway, these are we collect 1 photoelectron per 10 keV of energy deposited in liquid argon. There is a strong suppression of the background above the double beta decay with 2 neutrino, and the acceptance respect to beta beta is of the order of 93%. Here I show the plot, a similar plot that I have shown yesterday regarding what is able to do the liquid argon. You see that there is a strong suppression of the background in the region of the double beta decay with 2 neutrino emission. No suppression of the potassium 40 because it's an electron capture, no energy released outside in the liquid argon, a strong suppression of the potassium 42. And here you see the photoelectrons versus the energy and the triple lifetime, the stability of the performances, of the quality of the liquid argon. Okay, so now we apply the cut, this last cut, the anti-coincident, this argon anti-coincident cut, and what remain is the red histogram. One can also check the different role of the pile-shaped discrimination versus the argon. And here there is this plot which shows the A over E classifier versus the argon light intensity. And you see that they are completely, largely anti-correlated, and so they works very well. After applying these two cuts, we select these events in red at the end of the story. Okay. So now, after all these cuts, you can open the blind region, and this is what we have seen in the analysis region after the unblinding. So we end up with 7 events in this energy region, which can be translated in this background index. You see that we are slightly higher than the goal of Legend 200, which was 210 minus 4. So, of course, into sigma you are there, but we are not so happy, and not so happy due to this extra contamination that we have found. And now we are attempting to solve, cleaning the material. Okay, and here is the events in this analysis region, and you see we have an event near VQ beta beta. This is 1.4 sigma to VQ beta beta. Okay, but okay, this is the life. What we did is to combine in a single result the result coming from Gerda, Majorana, and from this 43 kilogram per year of Legend. What in terms of sensitivity, this is the sensitivity of this combined 3 experiment, and the half-life, what we observe is this one. If you give a look to the final result of Gerda. Final result of Gerda is 1.8. And here you see is 1.9, so there is no increase or improve. And this is due to the presence of these events. So because the fit say, well, maybe this is a signal, because it's there. But of course, we don't believe too much. No, we don't believe so much that we believe that is a true background event. But okay, this is the story. We can't do anything more now because on these events, because we are using a strict blind analysis, which say you did at the beginning a certain choice of cuts, and what you see, full stop. Okay, that is the last words regarding Legend 200 for using this first data, this almost 1 year of data taking. The data taking was stopped, as said, in February of this year, due to the fact that we have found this extra contamination. And so we decide to stop the data taking in order to understand the origin of this extra contamination. And so we perform a dedicated run in order to see the culprit, or more than, of course, there is as usual, as usual, as happens very frequently, we have a single culprit. We have various culprits, so the situation is not so easy to manage, but we are attempting to manage, reanalyzing, so making the screening of all the material. And now we are reassembling the detector, and hopefully we will start the data taking end of December or in January, not far from now, with a detector with hopefully an improved background situation with cleaner material, and also with slightly higher mass, no more 140, but 150, not the goal of 200, but with a detector, we hope, with much more reliability. Okay, this is our goal that we will perform very, very soon. So very soon we will restart the data taking. Okay, this is the end of the story for Legend 200, and we will see what will happen in the future. Now, some words regarding Legend 1000, which is the ultimate stage and the end of my lessons, if you want. Okay, what are the parameters, the performance parameter, and also a timeline when this experiment will be built, at which time? Okay, these are trivial. 1 ton of material. This is the energy resolution at the Q beta beta, 2.5, full width at maximum. The acceptance, the total exposure of around 10 tons per year, which means roughly 10 years, but much probably more, of course. The background goal is this one, 10 to minus 5 counts per keV per kilogram, that with this full width alpha maximum is translated in this other formulation. If you don't see anything, these are the half-life for the discovery and for the sensitivity. And translating, these are the effective Majorana mass for the discovery and the sensitivity. These are the goal. Now, when? As you can see, the design already started. We were approved as at the level of conceptual design. Now we are working in order to make more solid the design. So in an optimistic scenario, we should be able to start the data taking in some month of 2030. Of course, not with 1 ton of enriched material, but with some kilogram of, so some 100 kilogram of enriched germanium detector. And only here, in after 3-4 years, after the starting point, we will have the 1 ton, and we will have the full data taking. Okay, but in this between 2030 and 2033, we collect a lot of statistics. Okay, this is the technically driven schedule. Okay, the best that we can do. Okay. How looks like this experiment? Similar to what we have shown before. Only that the dimensions are larger. For example, the water tank has a diameter of 12 meters, and this big cryostat has an internal diameter of 7 meters. So a larger tank. You can, if you compare Legend 200 to this Legend 1000, you realize that there is a big, some differences. The first is the presence of this reentrant tube. This is a tube which divides the argon into region not communicating. This and the remaining part. Inside this reentrant tube, there will be this the string of detector, and each string of detector will have its own liquid argon instrumentation. So this fiber around the single string, which is slightly different with respect to what we had in Legend 200. We have in Legend 200. The other news is the fact that this reentrant tube will be filled with a special argon, liquid argon, a so-called underground liquid argon, which means a liquid argon in which there is in which the argon 39 and hopefully argon 42 will be reduced, and we will see why. Of course, the reason that is in order to improve the suppression, to eliminate this background, but how we can obtain underground liquid argon, I will say later. And then all the other part of the volume of the cryostat is filled with normal liquid argon, so liquid argon extracted from the distillation of the air. Okay, this is normal liquid argon. We call atmospheric liquid argon. Inside this atmospheric liquid argon, there is this special device, which is a box which surround the reentrant tube, is made of acrylic plastic, and there are around some light guides in order to detect the liquid argon light. The reason of the presence of this new detector is in order to mitigate a new background. Due to the fact that we go very low, we want to reach a very low background index, some sub-leading background, which are not important for Gerda, are not important for Legend 200, becomes important for Legend 1000. Due to this very low background index. This background comes from neutron produced by the showering rays, which can interact, absorb by germanium 76, become germanium 77 or germanium 77 metastable. This decays and produce a background at the Q beta beta. These two backgrounds, especially germanium 77 metastable, we are not able to suppress with normal cuts, germanium and the scintillation. So you have to tag in a different manner using delay coincidence, spotting their time decay, but also using other detectors in order to have other knobs. And this is one of the knobs in order to suppress this type of background. If you don't suppress this background, Legend 1000 can't be realized at LGS, because for the low level of this experiment, the depth of Gran Sasso is not so deep. You have to go even lower in underground, okay? Because the rate of remaining rays is too high. 3,500 water equivalent, meter water equivalent is not enough. You have to go even deeper. So this is the reason. Okay, the other, here there is the water tank instrumentation, which is more or less the same as before. Okay, so now the underground argon. So in argon, in liquid argon, for example, you have two long-lived radioactive isotopes, argon-39 and argon-42. You see that they have a long half-life. They are produced, if you extract this argon from the air, you see there are these two isotopes because they are produced in air. And so they are contaminants. Argon-49 is a beta emitter with a Q value of this size. It's not important for neutrino double beta decay experiment, but is of huge important relevance for experiment searching for dark matter using the argon. Dark side is an experiment using argon, and so this is a very important background because its specific activity is huge, 1 becquerel per kilogram. So if you have tons of liquid argon, you understand that is a huge background. Argon-42 is our specific background. As I said, as a limited Q beta, Q value, 600 keV, but then the daughter is the potassium, and the potassium has a Q value above the Q value, and this is our huge, possible huge background. In effect, its specific activity is very limited, but due to the electric field, we boost this activity, and so it becomes a background. And so this is the situation, bad situation. Now, dark side, the dark side collaboration has found the possibility to obtain sizable quantity of argon, not using argon from the atmosphere, but argon coming from mine. So argon which remain for forever or for a lot of time underground without any contact with the cosmic ray. Okay, so this spatial argon contain a limited amount of argon-39. I repeat, dark side is an experiment searching for dark matter. And here, in this plot, I show the result from dark side 50, which is an experiment of dark side using a limited amount of liquid argon. This is the energy spectrum. This comes from the S1 signal, you know, from the previous lesson of JJ, what does this means. And you see that using atmospheric argon, you have this huge contamination. But if you use underground argon, depleted in this component, this is the size. So here they have found that the suppression is of order of more than 1,000. We don't know if this underground argon, what is the suppression factor for the argon-42, because argon 42 is difficult to measure because it starts with a very doesn't start from 1 becquerel but from 50 microbecquerel. But anyway, due to the fact that also argon 42 is produced from the interaction of a cosmic ray with the argon, we assume that the contamination will be very the contamination argon 42 will be strongly reduced. Okay, this is the story of the argon 42. Said this, then you have to collect this argon depleted argon underground, and we will use what as a legend 1000 we will profit of what dark side collaboration developed. So dark side extract this underground argon from a mine, a CO2 mine in Colorado. Okay, this mine contain CO2, and this CO2 is used in for example, in the petrol for the petrol fracting, for the extraction of petrol from the rocks and so on, fracking. And in this CO2 gas, there is a small percentage of argon underground, so it is collected here and then sent to in Sardinia, where there is a building in order to purify to chemical purify this argon, and then this purified argon will be sent to Gran Sasso. So this is the chain. Here you see where this is the photo of this mine, of the surface part of the mine. The facility which for the argon extraction will be built here in this part, and then this argon depleted will be stored in this container and sent to Sardinia. Okay, and in Sardinia there is a coal mine, now not more used, in the Carbosulcis, and there is a very deep shaft, 350 deep, and here there will be built, or is building, a column for the distillation and purification of this argon, okay, in this facility. And then this gas, liquid argon better, will be sent to the Gran Sasso. Okay, said this, assuming that we will have this underground argon with a reduced percentage of argon 42, what are the background projection of this new experiment? Here in this plot is shown this energy region. This is an energy plot, and after all the cuts, and after 10 years of data taking. Of course, you see this part is dominated by double beta decay with 2 neutrino, the various background components, and here it was put a double beta decay, neutrinoless double beta decay signal, assuming an half-life of 10 to 28 years. And you see that, in principle, we are able to see this signal. Now, here the usual breakdown of the various background components. The this muon induced is the background coming from the fact that the muons produce neutrons, and the neutron can be captured in germanium-76. With the use of these new detectors that I have shown, is able to limit the contribution of this background at this level. Otherwise, this would be above 10 to minus 5, well above. Here you see what will be the situation for the liquid argon, for the potassium 42, using this new argon. Okay, so now the projected background index after all cuts is around 10 to minus 5 counts per kilogram per year. Here is a propaganda plot, if you want. So how it looks like a signal if we will have the happiness to find a signal, assuming that an half-life of 10 to 28 years. There are few number of events at the right position, and here you see how it looks like the background, if you satisfy the prescription of 10 to minus 5 counts per kilogram per year for 10 years, blah, 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 blah. Okay. Okay. So now this is another plot which show the comparison between 3 experiments, Legend, Cupid, Nexo. There is not next, but it's for some reason that is not important to say. This is done in this manner, this comparison, which say at the end of the story that these 3 experiments, at least theoretically, are more or less the same, so are not one better than the other, at least from this plot. They are built in this manner. They use the discovery sensitivity of this experiment in order to build these points. This point give the m beta beta at 90% at this level, 3 sigma level of discovery sensitivity, using this formula in which m is the nuclear matrix element, and you see that changing the nuclear matrix element, you obtain different m beta beta. Okay, the line here is the bottom of the inverted Auroy hierarchy with 1 sigma, 2 sigma, 3 sigma uncertainty, and you see that despite the large uncertainty coming from the nuclear matrix element, we are able to scrutinize the entire inverted Auroy hierarchy. Okay, this is the end of my lesson, of my slides, but I would like to end with 2 more, only 2 more, which are, up to now we have spent all the time discussing that double beta decay without neutrinos, which is the goal, full stop, no matter. But I have to say that all these experiments searching, having this monolithic goal, is also possibility to do something else, some other exotic search. And here I have put a list of topics, other exotic topics that were done and so also published by Majorana and Gerda, and also CDEX, which is a Chinese experiment. and here you see the type of physics, exotic physics that can be done with the data collected by this experiment, without any spatial data take, are byproduct of the main analysis. Okay, and here is a cartoon showing some of this result. For example, this is a result from Majorana and Gerda. Majorana is this red curve, and Gerda is this one or this one. This is a search for dark matter, super WIMPs, as a function of the mass of the super WIMPs, and these are exclusion plot, so the region above this curve are excluded. You see what can be done. This is a search for charge non-conservation made by Majorana, searching for this decay of electron into electron neutrinos. A signal should be seen here around what is 11.1 keV. Okay. Here another plot from instead Gerda. It's possible to search Majoron emission. Majoron are Goldstone boson, which can be produced. Or you can check the Lorentz violation. And this could be visible due to the fact that they produce a distortion in the shape of the double beta decay with emission of two neutrinos. Okay, others. Here is another plot coming from Majorana. Here, searching for lightly ionizing particle. That can be done also, for example, in this experiment. So this experiment can produce also other physics different from neutrinos double beta decay, even if by far, the goal of this experiment is neutrinos double beta decay, but is not only, there is not only double beta decay, but also other. Okay, that is.
This was your last lecture on detectors. Tomorrow you will tell us a bit about some techniques to measure the potential at some point very low levels of electricity and hard to assess the level of so there are specific measurements and we reckon it would be nice to just an overview of what is the sensitivity that one can obtain on measuring the relativity. The relativity is one of the biggest components in background of all this business seen throughout the last. So, unless there are questions.
One is just curiosity.
Yep.
How many years in how many years we expect Legend 1000 to work? And the second one is more complex. What if Legend 1000 doesn't see anything? Then makes any sense to continue the research, because for going to the next, to the normal mass order,
Next.
how much we should
So, regarding the first question, I can only answer showing another time this time scale. Oops. This is the scale of Legend 1000, assuming that you have money next year, essentially. Or if you don't have money this year, you shift in a rigid manner the time scale. Very simple. But I am saying that apart from the T0, which depends not by me or by you, this interval of time are reasonable, but you have only to shift. This is the first question, the first answer to the first question. Regarding the what next, if you don't, if this experiment of this new generation, future doesn't see anything, of course, if you, if the theoretician, the community, scientific community at the time are convinced that anyway you have to work because you have not fulfilled the entire phase space, you have to do better in some sense. For what concern the germanium detectors, so this technology, of course, you have to increase the mass, lower the background index, but this is true for all the techniques. So the answer is it's very, very, very difficult, but you have to enlarge the mass and to decrease the background. You have no. Then is how to decrease. Are you able to decrease, for example, for the germanium detector? I am saying technology. Are we able to go lower than 10 to minus 5 counts per K? The answer is I don't know. Honestly speaking, because no, that is difficult. So we don't, in some sense, our approach in Legend to have this stage approach is in order to don't to be solid, to make one step after the other, because we know that it's very easy to say, well, I will reach 10 to minus 6. It's easy to say, but then to realize in another story. And in order to go to 10 to minus 5 counts per keV, you see how complicated we think is, and we will see. And but apart to, so we have we started, but very, very in a very weak manner to give a look beyond the 1 tone. Of course, putting 2 tones, 3 tones, but apart, so, we didn't do much more. So for us, in this moment, realize the Legend 200 and the goal of Legend 200 and realize this Legend 1000, from my point of view, is already a lot, especially if you give a look to the time scale. Schedule, yeah. Then there are other approaches. For example, JJ will talk about the barium tagging, which gives a knobs in order to reduce to 0 the background, but is a technology, a dream that they are attempting to. We will see.
His question is interesting in the sense that Claudia Ortuao, not here now, but we were discussing that at the end of Claudia's lectures. It seems so and so on. And Joao came up with a nice thing, which is taking back what he was saying. So you have this two patterns. The lightest thing is really so light. Then you are given difference. And you say, okay, essentially Legend 1000, next HDD, copy the full array, and so on. They would like to target this 1028 or the equivalent in any data data. So you take away the factors because at least you get the level where you can exclude the thing. Then there is a jump. And God only knows how to get there. However, one has to keep in mind that this plot has been done on the idea that if you observe the neutrino decay, that is sufficient to claim that the neutrino is fully Lagrange, and that there is nothing else. If instead you have, and I think we discussed also with some of you, I think you've seen that with Claudia, that you have this black box theorem where you have lepton flavor violation. If you observe it, it's lepton flavor violation. It's not necessarily true that it's dominated by Majorana. You have level 10 to the minus 12 electron volt masses given by the Majorana part, and then the rest is Dirac with some beyond the standard model physics, still in the Dirac platform, say framework. Then you, yes, or in other words, at the same mass, you would sit at the m beta beta equivalent at this point, which is an effective m beta beta, no longer fully Lagrange, which is in the white part, in the no man's land between the green and the red. So in some sense, if they were saying, Joao, for example, was saying together with Claudia, if you, for example, make the effort of going to 2, 3, 5, 10 tons, or you manage to get the background index much further down, so your sensitivity increases not quite to get to the red, but still to get a bit beyond the white, you might still be lucky, because if you observe then what that is a different business. That's, for example, Claudio was saying, there was the super Nemo idea of, for example, measuring the angles between the two outgoing electrons. So you need additional information than just n beta beta. But the way we spin it, which is either we see something in 1028, or we have to make a huge leap of faith to get to the red, it's not quite exactly the same. In theory, if we saw something white, to get this down.
But if I have to say, from the neutrino double beta experiment, we see this plot projected along this line. For us, this is nothing, okay? So this means that if an experiment, the next generation, reach this, exclude this, the green part, but also large part of the green. So if we reach this, we are already excluding 50% of a normal hierarchy. So that is, yes. So maybe I have.
How many experiments you run?
Million experiment, and then
No,
when you run one particular experiment,
no, I don't.
okay, I translate now the way that I make a discovery, right? And it's very common.
So in the plot, there was also the assumption that the nature is not bad, in the sense that the plot that this usual Vissani plot assume that there is a possibility of a fine tuning in which you have m beta beta down to 0. But this is a really fine tuning. In the plot that JJ showed, this fine tuning is in some sense excluded because oops, this one. So this very low m beta beta is obtained if you do a very fine tuning using the two Majorana phases. So anyway, I think anyway, saying this, you see how difficult and how many decades we will spend in order to reach more or less this level. And I don't think that we will do a jump to this level, but we will improve.